today we want to talk about the determination of enthalpy, the heat of reaction using bond energy calculations, bond energy values. Bond energy, as it says up here, is the amount of energy that you need to break 1 mole of bonds in a gaseous covalent substance to form products, also in the gaseous state. Now, temperature, pressure, those have to be constant. So determining bond energy is not an easy thing, but we have tables that give us all of these values. Now, when bonds are broken, you have to add energy to the system, and that should make sense. It has to be an endothermic process when you break the bonds. To break anything, you need energy. When bonds are formed, energy is released, so that's an exothermic reaction. The equation is going to look like this, that the heat of the reaction is going to be equal to the bonds that are broken at the beginning minus the bonds that are formed at the end. Now, what this ends up doing is resulting in something exactly the opposite of all of the other equations we've used for this. Instead of being our normal products minus reactants, this one, and only this one, is reactants minus products. So when bond energies are involved, and it tells you energies of bonds or gives it in some kind of terminology like that, you have to remember it's reactants minus products. So looking at this example problem down here, we want to use bond energies to calculate this particular reaction. We've done it before with our heats of formation, but now we want bond energies. So this time, the heat of reaction is going to be equal to the sum of the reactants minus the sum of the products. I almost can't even write it down because it's so unusual to use that equation. We're going to do the same thing. It gives us the values down here for bond energies that we did for heats of formation. So for a hydrogen-hydrogen bond, it's 432 kilojoules per mole. For a fluorine-fluorine bond, it's 154. And for the HF bond, it's 565. And since HF is simply a 1-bond compound, all we need to do is multiply that value by 2 to see how much energy is involved there. So please use your brackets. This one, in this particular case, it doesn't matter as much since there's only one product, but it could in other problems. So we've got a sum of 432 plus 154. And we're going to be subtracting 2 times our 565, which gives us 586 minus 1130. Gives us a grand total of 544. Now we want to come back and put in our units. We often leave them out in this particular type of problem because they're all the same anyway. Kilojoules per mole, and since this is heat of reaction, the reaction of the entire equation for this particular reaction, we're going to put kilojoules per mole Rx in. Now be careful on this one. This one is a little bit different from heats of formation because let's say that instead of that 2HF, it had been 2 H2Os. In this case, if we knew what the HO bond was, we'd have to figure out how many total HO bonds there were. And remember, water looks like this. So water has 2 bonds, 2 HO bonds, and there are 2 of them. What would we have to multiply water's value by? Well, in the case of bond energies, we'd have to multiply it by 4. So keep that in mind if you're dealing with any kind of compound that's not just a single bond compound, that you have to add up the bonds inside it and then multiply by the coefficient in order to come up with the correct value.